I'm very pleased to present the final panelist of the morning. Benjamin Ennemoser is an assistant professor of architecture at Texas A&M University, where he leads the research lab for artificial intelligence in architecture. He has previously taught and lectured at UCLA, the University of Innsbruck, and the University of Applied Arts in Vienna, among others. He studied architecture at the University of Applied Arts in Vienna and the University of Innsbruck, where he graduated with distinction. He has received several fellowships and grants, including a research grant from the Academy of Performing and Visual Arts at TAMU, a CRS Foundation Probes grant, and the START grant from the Austrian Federal Ministry of Arts and Culture. His research on computation design, robotics, and artificial intelligence in architecture was published and presented in international journals, books, conferences, and academic institutions such as the AA London, Bartlett UCL, Tongji University, EPFL, and Taubman College of Architecture and Urban Planning. He is a licensed architect in the European Union and founded his practice in 2016. He recently collaborated with Google R&D for the built environment, Carvana, and Gensler DXD as a technology consultant and design lead. His topic today will be on latent manifolds.
Awesome. Hello, everyone. My name is Benjamin Ennemoser, and thank you very much for the invitation and having me in here. As Lee already mentioned, I'm from Texas A&M, and today I will show an array of research that includes some early attempts that we did at UCLA when I was back there, and some of my also work from my studio, as well as developments of the last years, including projects, publications, and research that is also developed with my research partner, Ingrid Meyer-Hufnagel from the University of Innsbruck. To contextualize a little bit where we are operating, I situate this work and research within the fourth industrial revolution, where multiple devices and humans collaborate with each other in an ecosystem of technologies. And for example, here, where we see an ecosystem of technologies within the fourth industrial revolution that are capable of demonstrating awareness of space and each other's existence autonomously. So we see nonlinear behavior of individual agents and components with the system, which is based on an increased intelligence of such elements, agents and also actors again. And in tandem of that shown, technologies, and as part of the fourth industrial revolution, artificial intelligence and more specifically machine learning are part of these ecosystems of technologies. In that context, my research focuses on how machines perceive, analyze, and also generate the built environment and differ from conventional parametric and computational models. And I'm just throwing this chart out real quick. You will hear me throw around with different terminologies, umbrella terms of artificial intelligence, down there machine learning, as well as deep learning. And I think it's important that we just contextualize that just a little bit in the beginning. So, and it's also important to note that in the research demonstrated in this presentation, we will see mostly unsupervised learning systems that speculate on their potential to extract and hybridize architectural data. And this is a very general overview, but nevertheless, I like to show this slide, to show the widespread applications that AI already has on our everyday lives. And just going through a few, from medical image analysis to driverless cars. If you have seen a Tesla, AI has seen you, all the way to weather prediction. If you Googled this conference, most likely an AI bot helped you in the background, and so forth. So the implications are wide, and they're here. But to roll back for a second, this was some early research by Google exploring generative adversarial networks, or short GANs, which is a class of unsupervised learning algorithms. And these images made me very curious and also initiated my personal interest in research in AI and architecture as an analytical and generative tool. We all agree that these are depictions of a goldfish, but clearly have interesting features we haven't seen before. Instead, we observe a distortion of elements, a hybridization of function, yet following conventional norms and features that yield us to agree that this is a depiction of a goldfish. To me, even probably the most interesting goldfish I have ever seen. To go even further and to investigate how, for example, generative AI can be utilized for architecture, we can look at this example and the use of GANs. And I apologize to everyone here who loves dogs, and this might be a little bit disturbing, but it proposes a very interesting concept to hybridize various taxonomies, species, typologies into emerging depictions. With a non-binary and, most importantly, non-linear yet manifold notion that derives from the latent space, which is the premise we will explore moving forward to this presentation. And obviously, the top right and the bottom left is not really where I feel we should lay or we should try to do our research, but it's right in between this seamless blending and interpolating in between, which occurs definitely in this example and in the later projects. In my research, I distinguish the use of AI in behavioral and generative AI. Here we have two examples we explored at UCLA around 2017-18. Left, you see an example of AI using ML agents and game engines, while on the right, it is trained on artistic influences and generates new artificial depictions of architecture, which in this lecture will be mostly what we speak about in that sense. To go a little bit more in detail, in this example from UCLA, multiple iconic buildings in downtown LA were selected, and the machine was tasked to generate the existing architecture into hybrids with artistic influences outside the field of architecture. That being said, we use different media artists, sculptors, and painters, and fashion designers as stylistic precedents with style transfer. The buildings were transformed into strangely familiar new depictions in, again, the style of the precedents. The aim is that architecture cannot live in a vacuum and has to collaborate interdisciplinary with other creative fields in this specific design studio that we develop with the students. And also, I think in that sense, important to note, in 2017, these application is far behind what we can leverage today with Google Colab and cloud-sourced machines, and it was obviously a pre-trained system. But we can go even further and train machine learning algorithms to semantically detect features and translate them to other typologies. For example, here in the video you see a cycle GAN that was trained on horse and zebras. I think we're all aware about the example. On the left, the original image, and then the machine is able to transfer the horse into a zebra to its best knowledge. Although this is called semantic feature translation, the machine has no knowledge what a zebra, a horse, a building, a city is, but it forms an understanding of a subject in the latent space by analyzing data and its features. And in this regard, we also come to the core of machine learning and AI process, namely data. And this is, for example, the data set the algorithm from before was trained on in order to transfer the features of a zebra to a horse. And working with vast, messy data sets, we are not just working with different form of data as conventional computational algorithms, but we also have to raise the question of bias, data diversity of the data, and of course, the authorship that we as architects take in that role. And this is an example of an excerpt of an architecture data set, an eclectic selection of buildings that you get when you type in a modern house in Los Angeles, for example, in Google. But again, it resembles the same structure as the data before. And here, I think very important, talking about authorship and agency, the architect assumes a role of data curator. More to that later in regards also to Heinrich Wölfflin, as we'll talk about it. But by selecting the data and collaborating with the machine in terms of human machine learning, and then working especially with GANs, who has generators and discriminators, there is this interplay between the forger, the critic, or however these generative adversarial networks are explained. And this premise was explored in the research project ML City, exploring GANs in combination with architectural data. This research also made its way into machine learning at the city by Color Scarpa, and is using vast amounts of satellite images, data from remote sensing technology, including cities, landscapes, and the built environment from, oops, the video is not playing. There was a video. And I'm in particular also interested in how the machine perceives, analyzes, and generates the architecture through its own lens that differs from a human point of view. So for example, pay attention how pools are deemed as essential elements and that are from the Los Angeles data set and are incepted into the Barcelona block along with suburban features. And you see how Barcelona and LA clash into each other and create a new proposal of a city with different densities, structures, ratios, and so forth. Or how plant versus grown architectural structures, like here between Marrakesh and Barcelona, might create a new taxonomy of architectural elements. Marrakesh's small courtyards and deep courtyards fill the outline of the Barcelona block, while clear axis and orientation persist in these outcomes. In this example, even multiple cities such as Delhi, Los Angeles, Portland get trained, perceived, and also hybridized into each other, where specific features, elements of each precedent persist and also are, again, traceable. The same with Portland, that turns into a garden city, keeping the suburban distribution, the grid, that's the integral part of the latent space, also after training. And the same technique is deployed to explore in combination with a present issue, namely anthropogenic climate change. Here, where we attempt to train these exact same machine learning systems to predict climate change in specific areas, landscapes, urban or rural territories, and propose a solution that is adapted to that new reality. So therefore, we collected information and data from NASA and other sources to establish a prediction how certain areas will transform in the near future and what the impact will be. This was a seminar that I taught, and in this course, we attempted to establish a case and also find commonalities between current landscapes, areas, and future territories so that the machine learning system can be trained to predict environmental factors and find solutions that might be resilient to the changing environmental factors. And we applied these techniques to coastal regions like river deltas or marshlands here in Florida. Actually, some of my students were from Florida. They were keen to explore that. And in these case studies, we tried to learn from cities like Venice, Italy, Amsterdam, and so forth, which already have canals and coastal attributes or are fighting certain environmental factors, which are within the urban fabric. So the results demonstrate how hybridizations of these cities can be deployed towards impacted areas and propose a new built environment that holds the DNA of various precedents. Or if we look how Greenland will look after the ice is melted and becomes inhabited, to the prediction of NASA's data and models, we made a case that Greenland would look similar like Norway potentially, and use the deep learning process to depict rural areas to become wildland-urban interfaces. In this pursuit, we also investigate how these tools with remote sensing technologies, such as satellite imagery, we are able to develop planetary cityscapes. And here we have the possibility to expand the data set from Western canons or to vernacular structures through the help of satellite imagery. As mentioned, the diversity of data is crucial in order to also train it properly and get the proper results. This research was just recently published in the latest IJAC issue about data justice, where we claim that satellite imagery and remote sensing technology probably for the first time allows architects to access and create data around the globe that is inclusive and diverse without literally no additional cost, effort, or any issues, which would have been way more tricky before using these data. And here, a few more examples of planetary cityscapes that encompass a modern Western, but most importantly also vernacular topologies around the globe, harnessing the potential of AI systems to hybridize in the latent space. And once GANs generated and hybridized the urban fabrics, we manually evaluated and dissected these planetary cityscapes through classical figure ground analysis. And in result, we discovered that the classical figure ground analysis and form analysis might not be suitable anymore, but in consequence, we need to utilize other techniques and vehicles to evaluate for GAN-generated results in architecture and urban design. And in this trajectory, Convoluted City, that was just presented last week at Acadia and exhibited in Bologna last summer, also investigates how to evaluate, interpret, and read these latent manifolds. Convoluted City, in that sense, also asks the question of where the city starts and where it ends. What is the land we live on? In that pursuit, a multidimensional cartography is developed where for the first time an AI's latent space is translated into physical matter. And notably, no geometry, as in the previous voxel or 3D print, is needed. And in the notion of Map making is world building. Architects in the past have attempted to alternative and universal cartography to rethink planetary interconnections and relationships. And these practices approach a different reading and understanding of the planet we live on from a merely two-dimensional representation. The idea of convoluted city is to superimpose the artificial environment you live on top of the natural environment you live from and the waste landscapes you generate. Without such an overlap and the experimental computation between them, you will never understand or develop a sense of responsibility towards planetary interests beyond human survival. The resulting chimeric urban landscape should trigger your imagination to rethink urban ecologies and interspecies habitations that are beyond the human-centric modernist idea of the city. This is made possible by creating an unprecedented three-dimensional version of the latent space, not just as a visualization, but also as a physical matter that holds the entangled relationship of our environments. Before satellite data collection, we studied the interconnectedness between cities and their dispersed landscapes. In our method, true and false color remote sensing images were curated, and through the use of an enhanced color spectrum, a different way of seeing other than human territories is enabled. And using this research, we generate data sets for training a neural network, specifically, again, GANs. And with the latent space and manifold interpolation, the results geared towards intersections and entanglement versus difference. By using manifold interpolation between selected seeds, we created hybridized animations of urban landscapes, comprising 3,760 images for each. Is the video playing? Is it playing? Oh, here we go. Very slow. Oh, now it's playing. So these images were then utilized in 3D printing, where collaborating with Stratasys, we employed their PolyJet J850 and voxel printing technology. And each image was translated into a single layer with thickness of 12 micrometers, forming a vertical print sequence. This process entails dithering of the image data from RGB to a CMYK-WA, so that only 6 materials were used in such a high resolution that the gradation among them allowed a wide range of colors. And with the PolyJet's printing resolution of 300 dpi in the x-axis and 600 dpi in the y-axis, the images needed to be processed in a 2:1 rectangle ratio for accurate proportion, and resulted in 42 billion uniquely addressable data points for each model. So if these data points is directly translated into the physical matter. We also create a visualizer that helps us to predict and see transparencies and the distribution of these data samples. But unlike previous voxel print research, our approach omits geometry like conventional additive manufacturing and uses one image per layer instead of 7, but requires a dithering process for each GAN-generated image. And our results demonstrate a unique translation of 2D images into physical matter, eliminating the need of intermediate 3D geometry. And in addition to this technology, the temporal and spatial compression of an entangled urban landscapes enabled by the latent space develops an understanding of their interaction. And there is not one universal legend to read these maps from the latent space. It can be read on multiple different approaches. The reading from a traditional 2D map shifts to observing a 3D object. And the reader must expend substantial effort to decipher these models, which is inherent in the extensive data processing involved, albeit in a compressed form encompassing all data elements. And for example, the attentive observer will identify urban fragments, buildings, streets, grids, and so on in an X and Y layer, and how these interweave with landscape elements of a similar initial scale on another layer. A way of reading that is familiar to us and also would also prompt us to see other habitats from different scales, like insect habitats on similar layers required a change in scale. And this implies that we must abandon our habitual way of reading maps by means of universal indexed legends and encourage us to adopt more inclusive practices that advocate convoluting multiple readings into each other. And so far, so good. But in order to further understand how machines perceive and analyze and generate our built environment, I want to invite you to a journey on learning to see like a machine. That's a text that, and also a thought that I first started in this book by Ingrid and further elaborated. And I think also another speaker, Professor Vera Buhlmann, is also featured in that. But to go back to that subject, around 1915, Swiss art historian Heinrich Wölfflin famously elaborated on 5 pairs of formal concepts to classify and analyze paintings and their inherent style in his book, Principle of Art History. And almost exactly a century later, a novel form of machine learning algorithms like GANs, what we already heard about it, was invented by Ian Goodfellow, basically 100 years later. And GANs are unsupervised machine learning algorithms with the ability to learn from vast data sets and subsequently generate new depictions from a data set. When tasked to learn architecture data, the machine has no prior knowledge about architecture, nor will it gain any particular knowledge throughout the process. In fact, the machine focuses on extracting and learning essential features from a data set through a straightforward formal analysis. Based on that premise, the GANs and Wölfflin methods rely on formal analysis. This thought compares and highlights the similarities of Wölfflin's concept with the logic of how GANs analyze and generate architectural spatial compositions. We have discussed over the last few years, multiple GAN algorithms have been developed and increased in realism, fidelity, and control over the latent space and also the manifold results. And GANs are structured into 2 adversarial ML systems. One is the discriminator and one is the generator. And since Wölfflin only uses this technique as an analytical tool, we're also going to make the case how to use it as a generative tool. And so now back to this diagram, where I think it makes more sense for us being the curator, the forger, and the critic in the notion of Wölfflin. And this is also like I think a representative of how the data set is created, distributed. Even when it's biased, it will steer and influence the output and what features the GANs and what they deem to be essential within a data set. This scheme sometimes is also described as a cat and mouse game, but again, I think, in the light of Wölfflin, the curator and the forger and the critic fits a little bit better. And arguably, Wölfflin worked with very small data sets or even just pairs, individual samples for his formal analysis concerning styles, but he also consciously rejects the bias of regional influences or artist-specific nuances that he refers to as an artist temperament. That in return ensures distilling the essence of contributions to a style when applying formal analysis methods. So, for example, Wölfflin compares Baroque sculptor and architect Bernini with the Dutch painter Ter Borch, who both show painterly tendencies that suggest an association of style. For Wölfflin, both artists superficially don't share many commonalities, primarily due to artistic temperament. But through objective and formal analysis, associations can be traced. He makes a similar case study between Michelangelo and also the early work of Hans Holbein, which initially seemed distinguished by regional characteristics, but through his formal analysis share the underlying notation of the linear. So with GANs, we have vast amounts of data and samples beyond just pairs, so which I think is in our benefit. And GANs can also rely on experience initially, but build up in vast amounts of these data that is diverse and beyond just 2 styles that allow them to crystallize features and gain expertise on a very particular collection. Wölfflin uses his 5 pairs to analyze paintings, sculptures, and architecture, and the 5 pairs of formal concepts, namely painterly, linear, plane versus recession, closed versus open, multiplicity versus unity, and absolute versus relative. But in this concept, in this research, the first 2 concepts, linear versus painterly and plane versus recession, emerge to be the most inherent advocates for similarities in Wölfflin's and GAN's formal analysis in pursuit of extracting and categorizing essential features from architectural data sets. Although obviously in architecture we could trace all 5 of them. So moving forward, Wölfflin stated in an essay, learning to see is everything in the context of evaluating epochal styles. And GANs have the ability to see and analyze a data set and extract features through a series of machine vision operations. But here the question arises, do we need to learn to see like a machine when working with machine learning tools in order to understand how architecture and the built environment is perceived and generated through the lens of the machine? So therefore, this research demonstrates how machine vision processing, contemporary GANs and Wölfflin pair share a similar formal concepts. But Wölfflin doesn't just state we need to learn to see, but also explains that to conduct formal analysis, we need to examine an art piece through multiple visual layers, which naively also shows tremendous familiarities how a GAN, for example, works, and a GAN analyzes data samples. And looking behind the scenes of GANs, we rely on features visualization techniques to evaluate these results. Features in the realm of machine learning and machine vision are patterns that can be isolated and detected from a data set. Here we see, for example, features visualization of the Barcelona block through a formal analysis of linear, painterly, planar recessional concepts. And features are extracted through this sequential formal machine vision process in visual layering, where also there's a certain level of abstraction happening in order to extract the patches and the elements. And while we can visually determine the traces of Wilflin's formal pairs in results and by looking behind the scenes of GANs, it is also crucial to quantitatively assess how machines perceive and generate our built environment. So GANs are unsupervised systems to evaluate how they perform analysis. We use unsupervised machine learning systems to evaluate and visualize them, how they extract and also transfer the features. So basically we use an ML system to evaluate the results of another ML system. And as part of this qualitative evaluation process, we look for residues and leftovers of features from the original architectural data set. More precisely, we reflect on linear, painterly, plane and recessional features. And for example, we can see how Barcelona's block, again, clearly linear features that is filled with linear, painterly suburban houses from Los Angeles. So while there is a clear linear, painterly formal analysis between these data sets, it is also remarkable that specific features such as pools from Los Angeles are detected as the features and transferred into the Barcelona block. Or on the other hand, where Marrakech's courtyard again have these recessional features of depth that push back the planar perception and suggest depth on top of linear and painterly features. And in this process of evaluating, we can create a catalog of linear elements across scale, or similar with painterly elements, a whole series of elements that emerged that serve as a blending between linear and painterly elements. Or when we use supervised machine learning algorithms to do a more in-depth and quantitative evaluation, feature visualization of the Barcelona block or the Portland and Marrakech, what we have seen earlier. And linear and painterly can be traced to a supervised machine learning process. Equally, we demonstrate also here that through ML-aided depth map analysis, also the concept of plane and recession can be extracted, trained, and generated through the lens of the machine. And here again, we are demonstrating that the concept of plane and recession, or simply depth, is an integral property of GANs. It is evident that depth is preserved from the data set and transferred also into this new hybrid composition. Let's see. Here we go. So now going from 2D pixel to 3D models, from image data sets to 3D models, and also into point clouds, or basically from 2D pixel to 3D voxel. Oh, now it's not showing. The next, here we go. So although the image data sets are still the most dominant form of samples used in GANs and architecture, we also investigated how to train 3D data sets instead of 2D images and the relationship between Wilflin and how GANs evaluate these 3D data sets. Going into a more applied project, this was a commission and the first attempt to do 3D GANs for the Yanitsky family in Marina del Rey in California. And here we see a modern house 3D dataset being streamed into machine learning process. And this first attempt relied on synthetic dataset because there was literally no proper, and still to this day I don't have a proper housing dataset due to the scarcity of these models available. And once elaborating on that project and then whatever as a structure and an outer shell the machine spit out, there are clear cutouts from the synthetic dataset that are deemed to be essential. But at the same time, also we see how other like smaller details like the railing and the louvers and the facades are coming through, which obviously have a direct relationship of the 3D data set. And Wilflin's application of his formal principles works with 2D images, but also if we try to evaluate it with 3D models to help us to evaluate the results from these 3D GANs methods. Regarding to our 3D GAN experiments, no matter if we are working with synthetic or manual data sets, which we started to do just recently, there is a linear versus a painterly negotiation between spatial elements. And it becomes evident that certain elements and features are translated very linearly, while other elements are being hybridized. And this initial process of 3D GAN was also further developed into a process that initially triggered the shift of training of 2D voxel and 2D pixel towards 3D voxels. A shift that also relies again on data diversity, the latent space, and manifold interpretations. And we use the technique of voxelizing not just the exterior shape, but also the interior sequences of building models. And that was also in the same part of the same IJect, also published there recently. And in order to investigate how machine learning hybridizes or determines linear elements in 3D GANs from the latent space and manifold interpolation, we can utilize again a supervised machine learning process with labeled 3D data sets and trace the reading of the machine of the built environment. More precisely, labeled topologies, architectural elements, and materiality, especially when we work with point clouds, allow to not just train multidimensional layers or information, but promoting this hybridization and also trace the AI's process. Okay, the video is playing also. So this leads us to conclude that clear boundaries or cutouts in the resulting 3D models follow a linear nature. There is no painterly nature in blurring or gradually blending with 3D GANs. In contrast, painterly is applied when elements and sequences are being hybridized. So changing from 2D to 3D data sets, from pixel to voxel, blurring or blending is replaced by hybridization. And to close the loop, of how AI generates latent manifolds, we need to look into the concept of interpolation and how that has shifted from the first to the second digital turn. A line of thought that recently was just also presented a month ago at EKD by Ingrid and myself. And let's begin with a historical perspective. Consider the structural beams of the Sydney Opera House as an early example of linear interpolation, where beams transition continuously from a U shape to a T shape. But during the first digital turn, linear and geometric interpolations achieved remarkable advancements. And here what you see, a video on the screen. Greg Lynn's embryological house serves as a prime example, showcasing infinite variations with the same typological form. That means remaining within the same genus. So let's take the minced digits, which is often used in deep learning and which you see on the left below. Linear interpolation between two samples does not produce a minced sample, but blurry images, and the same holds true for architectural examples, or if you do a linear interpolation between building footprints, like a slab and a block or a topology. So you do not receive a plausible form, and everyone who has tried this knows that you have to cheat by creating either self-intersecting geometries or generating the illusion of variant genus in the geometry. So, but when we're using manifold interpolation from the latent space, valid results occur even between different topologies. The fascination in regard to latent space lies in this compression of data points and example input data, whereby previously unobservable linkages across topologies and scales become tighter and thus visible. In other words, huge data sets are ordered and simultaneously compressed based on similarities. The emphasis here is on the plural. That remains inaccessible to the human eye or cognitive abilities. It revolves around deep learning's potential for manifold interpolation across diverse building topologies of different cities and across scales, means making use of the ability of the machine to process vast amounts of data. And therefore, we're investigating about the existence of topologies invisible from human perception due to a data processing limitations. Through manifold interpolation, we have unveiled results with typological variation that are impossible to generate through the linear interpolation methods. And a walk through the latent space gives us an insight of the manifold interpolation across various topological forms and Cartesian dimensions. So the 3D GAN results proves what we already observed in the 2D urban topologies, namely manifold interpolation seamlessly transitions between topological variant topologies that wouldn't have been possible with linear interpolation from the first digital turn. And to deepen our understanding of manifold interpolation, we also again have labeled the data sets according to building types. And our approach involved labeling topologies with different color ranges, enhancing label differentiation using RGB values. And in this interpolation process, we observe a significant deviation from conventional linear interpolation. Instead, the machine orchestrates intricate transformations akin to a seamless jigsaw puzzle assembled from multiple components of a larger ambient space. So consequently, to grasp the concept of interpolation with the context of deep learning, it is imperative to comprehend the nature of latent manifold interpolation as distinct from interpolation in a physical Cartesian system. This interpolation was characterized by dithering rather than linear interpolation, serving to index the elements and their relationship within the voxel field. This is a physical model that we created also again in collaboration with Stratasys that demonstrates the hybridization of topology, spatial sequences, and also materiality utilizing 3D data sets, and most importantly, point clouds. For this particular example, we are leveraging the high performance and research computing facilities at A&M, where we are able to train vast amounts of data and billion data points. And the results suggest that manifold interpolation involves continuously hybridizing across topologies of various genera and scales, resulting in spatial compositions that align more closely with contemporary living and working practices. So the research emphasizes the importance of accurate and precise terminology in the field of deep learning and architecture to avoid misunderstanding and to leverage the full potential of a new techniques and applications. Thus, this research initiates the search for an adequate description around manifold interpolation. And departing from the first digital turn, we resort in our research methods to concepts, to hybridizing and synthesizing until a deeper theoretical discourse around interpolation, its terminology is established. And moreover, the study showcases the utility of manifold interpolation and GANs in uncovering latent and hitherto invisible relationships between architectural topologies, proposing an innovative hybridization using machines. So leaving the architect, as indicated earlier, as the curator of data, trying to shape and control the latent space, which holds all possible depictions of what a machine thinks architecture looks like from these vast and messy data sets, until the introduction of diffusion models, right? A new architecture, and we're all aware about it, and I don't want to spend too much time on it, but we're all aware about a new architecture of AI tools that resorts from the latent space and latent manifold interpolations, but omits the architect as data curator based on the data set it was trained on. So we see a shift from data curation to prompt engineering, where models are trained on famously on the Latent data sets and billions of images, annotated images from the internet, where we potentially all have contributed to it very generously, but are also mostly reflected by popular culture. And I'm just going to zap through these real quick. These are some examples of an exhibition that was invited at UT Austin that was called Architecture After AI. And I asked the same questions about a modern LA house as I did in the 3D GAN or Yamitski house. Just in this exploration, it is triggered by text prompts that describe or ask for modern house in Los Angeles. And there are forms like imagine a modern house in Los Angeles with columns, ornate, mycelium, white color, plaster, or brutalist architecture, modern Los Angeles house, just a series of keywords, or even a modern house in LA aggregated from wood joints, or a modern brutalist house, decay, irregular, and so forth. But in a more depth investigation on how latent manifolds are generated is carried out, is examined in the project Diffuse Countryside. This is a project that was funded by the Academy of Visual and Performing Arts at Texas A&M with the intent to promote the arts in the Brazos Valley. Therefore, we ask the question, how are rural settings or vital and urban interfaces represented in pre-trained diffusion models, and how can we again extract these latent manifolds? And this, what you see here right now is that we made a survey of buildings and infrastructures in College Station, Bryan, where Texas A&M is. And these surveys serve as a building stock and housing for our case studies, starting to point and trigger these diffusion models. and demanding from the AI system to imagine these colonial, industrial, and southern housing stocks to be imagined in the fashion of contemporary style. So the project critically investigates the issue around data justice and also bias when developing diffusion models to generate architecture and its elements, and resulting in a composition of known and unforeseen latent manifolds, leaving us with deciphering traces that might derive from the data set and the model was pre-trained on. So yet we see the unfamiliarity that is forced onto the original input case study that is an indication of the underrepresentation also of wildland-urban interfaces compared to influences from popular culture and governing canons. And in almost an archaeological process, I disseminated these realities in the latest issue of UCLA's Pulse magazine, where I search to uncover the traces from the latent space that made up its multidimensional, constantly oscillating and also permanently changing state. It compares an AI model that are created by the architect and pre-trained models that are not created, but rather an agglomeration of digital footprints. So resulting in a search for traces, digital footprints, smears, and the DNA of data revealing that only the ones with the biggest digital footprints are considered while the others are left behind. And so to end up this journey, maybe we need to lean on Corpo once again. GANs and other AI tools basically start a formal search in a data set to extract these essence of architectural precedents and suggest novel depictions of manifold realities from a data set. This can be also compared with the concept that Mario Carpe iterates in his chapter Searched on Sort, which originally comes also from Google, where Carpe explains that there is no need to sort data or information through novel algorithms such as Google or Gmail searches. Instead, we can just task an algorithm to search and suggest what we are looking for. And by now, knowing that there are also machine learning algorithms behind these search processes, GANs and ML-based searches or any AI process suggest their manifold solution based on the machine interpretation and knowledge they have harvested from data and stored in the latent space. And what that offers is a latent space, what that offers is a latent manifold series of realities where each representation has its own justification, inhabiting the essence of diverse data samples, yet speculating on non-binary intersecting hybridizations. Thank you.
All right, as you know, he's not off the hot seat yet, but the observant ones in the audience will have noticed that the optimal strategy is to drag out your talk so there's no time for questions afterwards. But
we have half an hour, so go on.
Okay, so.
Sure. What was your last word? I really like the phrase non-binary intersecting.
The last word I will read from my notes. That's why I like notes. And what that offers is a latent manifold series of realities where each representation has its own justification, inhabiting the essence of diverse data samples, yet speculating on non-binary intersecting hybridizations.
Well, I just say why I asked that, because I think there's connections with my own thinking on binary architecture from a transgender perspective. And I think that the images you showed at the end, if we look at them from a trans theory lens, there's a lot that can be generative there.
Mm-hmm. Thank you.
Yes, thank you. One thing that I was intrigued about was how in your work you increasingly kind of cultivate this ever larger manifold, and you explore the latent space of it. And I was wondering, would that be, I was trying to step back and imagine kind of what would the brief be of an architectural project that would try to work this way with this or these manifolds. And I'm wondering, do you see the architectural project as something which lives in an ever richer, in the latent space of an ever richer manifold? And is the human, if we were to say there's kind of a moment, I forget the names you had, the discriminator,
the generator,
and the curator, is that where the articulation of the architect is occurring? And what happens when, because then you've built kind of you've built your latent space, or you've constituted it, and then you would be articulating a building project on top of that. How do you see that relationship?
I think that's a very interesting question, and I would say in an ideal world, this latent space, this training just keeps going on and going on, and we just feed more data in it, right? And yes, the understanding of an AI, no matter if it's 3D data, 2D data, empirical data, whatever data you just feed in, right? It happens between, at GANs at least, at this interplay, at this cat and mouse game, or the game between the forger and the critique, in between these two adversarial networks, right? So they somehow build each other up and then also try to give feedback. So what do we have you learned? What new came into the picture and what is most essential? Technically speaking, there are some issues to that, something called like overfitting and underfitting, where you cannot endlessly train, right? But if we leave that behind, and I think your question is more about the conceptual agenda, I feel like we as architects can assume the role of just like making sure that we collect the data and I tackle a project, let's say an urban project or a housing project or a building project, that I think is going to be essential or important in order to trigger these kind of like manifold outputs, right? So to your question, what the role of the architect is, I think it's very clearly curating the data set, depending on which tool you're working with. Obviously, what I try to point out as a small critique, but not about diffusion models itself, but whatever they are trained on, you go into prompt engineering, but you can try to engineer as hard as you want. There are certain moments when College Station Bryan, most of you have never heard of, but that's where Texas A&M is situated, is not on the map because our digital footprint is not great, right? While Los Angeles, oh, it's fantastic. The palm trees are coming up, right? The neon signs, because it also goes after data sets like Zillow, right? Or real estate. So I don't know if this answered your question, but I think it's about creating the data and being as responsible as possible, you know? And I just don't want to advocate solely in my research about data justice and whatsoever, but I also have learned from the very early start that by controlling the data, I can also get what I want as an architect, right? Because I also want to go for certain formal features. I also want to go towards a certain aesthetic. And I think that also goes a little bit back to what was asked earlier to Igor. I don't know where he is. He's over there. Like, who made the decision in that? As a designer, I still want to have a certain say in what the aesthetic output is, right? So I also try to bias it purposefully a little bit, and that I get what I want from that machines, which is not always the case, right? Obviously, I think diffuse countryside also showed like, do I really want that? Is that really the future of housing in rural Texas? I don't think so, but that's what the diffusion model thought it might be. I don't know if this answers your question, sorry.
Yeah. Obviously, the way that the models are trained are aesthetically based. That was a choice you made in the data sets. Is that the most necessary in the current world? Should we be looking at other data sets? And when you have a voxel, which is capable of dealing with a lot more data types than a two-dimensional pixel, should we be going in another direction? And is that a future for your own research now that you've developed these diagrams for human-machine interface?
Very good question. Yes, I think, in the early examples, and which were literally one of the first ones where there was an attempt between Barcelona and Marrakesh or Barcelona and LA, that started beyond an interest in formal features. That was literally curiosity. How can I cross-pollinate these two very different urban fabrics, and what would be a result of that? Like, how could Barcelona be cut down and have these deep courtyards that are coming from Marrakesh, or at the same time, how could a Barcelona block emerge in a different topology, urban topology, in a sense of like not this density, but LA suburban, would say quality. So there was a non-formal approach towards it, but obviously I also like the outputs to agree with. And you're absolutely right. There's so much more information we can label on it. And I didn't talk about it, but that's also the potential of remote sensing technology. Because what we see as RGB is just the tip of the iceberg of information that a satellite gets from each pixel in it. And the same is from with voxels, right? So we are starting now to train point clouds. And that's why we need to use the high-performance research computing resource at A&M, where we can train not just their location, not just their vicinity, but also way more information that we get from a LiDAR scanner, like color, brightness, and so forth. So yes, I think this is just a foundational start, and we're working on just like deepening it way more. That goes literally also in, I would say, what we start to tackle with convoluted city into material ecologies, but also seeing like how function and architectural elements could work towards like a different materiality and what is actually the reality from where we are drawing it. Yeah. But I think this is the next hot topic. Yeah.
So does that result in improved human environments?
That's what I hope so. But I think the problem is sometimes even simpler. I would train this model, and then the first step, I think the first challenge we have is to just understand how does the machine even train that. And then, once we have figured that out, then the applications are, again, manifold or widespread. But I completely share that trajectory, that I think that is the future, of all this research. Thank you.
So thank you, Benjamin. I really enjoyed it, and I really, it's a kind of formal exploration. I think I find it very successful. What are you achieving? And I'm seeing some new things that I haven't seen before. But I have a provocative question just to spark the discussion a little bit. So my question is, like we have number systems, we have natural numbers, rational numbers, real numbers. But to come from rational numbers to complex numbers, you cannot interpolate to get there. So you can try interpolating whatever you want. You will never going to get the complex number. Complex number is not a process. This kind of model could somehow learn from data, because all data has been described with a different structure in mind. So my question in terms of that, so to invent complex numbers and then the whole science of the 21st century, we need to have invention. We have to step out of what we know and create something radically new. My question is, can this thinking be asked to architecture? Is there still a role for invention in architecture rather than interpolation? Is there something there to be invented to put on the table as not seen before? And how can we even formulate it? What comes to mind is Corbusier, which I'm not saying I'm a fan, but I'm saying that Corbusier, when he created those forms, they were novel. But they were also, he created a man. He imagined a man to live in them. And he imagined a building technology to build them. So, so in that sense, can you?
I think very, very important question, and thanks for asking. To me personally, I think what we had talked earlier a little bit, like going away from binary descriptions of what an architectural element, an actual architectural function, or even materiality needs to be, seems to me very contemporary and very, very important to tackle. Does that yield to the groundbreaking new innovation within the field of architecture? I don't know. I can't predict. But there is a fascination for me that all of a sudden I can interpret data very differently with these AI tools than I was able before. But by me saying that doesn't mean that these systems are incredibly smart. At the end of the day, they're actually not that smart as we like to explain them. They can execute like very, very simple tasks. But yet, having this formation of human-machine collaboration, I feel like something new can be sparked, right? I mean, go back to Corbusier, he's not the only one, the first one. Also, the time he lived in and innovation and technology and whatsoever also formulated or were a vehicle for his concepts and architecture. And I feel like tackling maybe aesthetic forms of AI, or even just the idea of grasping larger amounts of data we were able to do before, or being aware about much larger issues like climate change and injustice, right, in this world, and being able to train that could potentially then yield towards something new. And I'm a strong advocate of changing the medium or changing the lens you look at, or changing your point of view, you look at a problem, usually is not a bad idea. You can't lose, right? Because you already have the views that you're biased in. So engaging with these tools and trying to get a different filter on top of it might yield to it, but I don't know. But I appreciate the question, because I think we should ask ourselves that every day. Why do we use that, right? I know. I appreciate the question, because we should talk about it. Yeah, thank you. Connor.
So, my question is about your last statement with Mario Carpo's quote
Right.
about search and sort. And I was thinking that maybe there is an extra layer on that, maybe architecture is not only about search, but about imagination. And I think this
Right.
relates a lot with what Nicola was saying. What will be architecture if we are now in this very powerful momentum where we see that these data-driven approaches are, like there, we can leverage that. So when you think about imagination in architecture, and then you go back to your latent space,
Right.
you are all of your work is beautiful and fascinating because you're imagining what this latent space could become. Now that you have really kind of synthesized maximum your data set that you created, then your latent space becomes this creative ground where you're imagining what can be. But I think I was just trying to feel how you will think about my way of interpreting your work, if this is what you're doing when you're thinking about this latent space and imagination and data curation.
Also, very good question. I don't know if I have a very clear answer to that. I mean, I always put out, I usually very often end with that Mario Carper slide, because it is controversial, sometimes a little bit outdated, but at least I like the idea of searching, right? And just to be very clear, whatever we see here, again, it comes back that the AI is not as smart as we might think it is, but we always need to collaborate with these systems, right? And by collaborating, no matter if I write a text prompt, if I create the data, if I bias it a little bit to be beautiful or formal or not so formal, I have certain agency towards this imagination. So yes, and I think it's very clear. I played it with my students. I let them use diffusion models. The first day they go into that game, if they don't have their own image in head or their own trajectory or agenda they want to get, they get no useful results from any diffusion models, GAN, whatsoever, right? So yes, it needs the human first who has a trajectory and agenda to go into this game when you create data, when you engineer prompts, which also yields us, to something which is great. And I know nobody here is afraid that AI takes our job, but it won't, right? Because I need to go in there and ask the right questions. And I don't know if this answers your question, but I think the imagination starts with the architect or the designer who tries to collaborate with these tools.
I know Adi is there, but Adi, we know that you're there, and you're gonna be next. I'm just thinking, this is very interesting work, and that's why I'm so excited and asking questions about this. Is that
I appreciate it.
I don't really think the machines are not smart. I actually think that they are smart, and what we've seen now with all of these generative algorithms is that they become this common sense. They really know. And I think this is something that we need to leverage. We don't have to treat them like slaves. They just create results. We have to engage in what you're saying, right? They should become agents or active agents that are really contributing. So if you already tell them you're not smart, then you're just putting them in a very, very not an interesting ground to play with them. That's what I wanted to say.
And I want to answer that. I completely agree with you. They're not. I didn't say they are dumb, right? I said they're not as. And but when you think back at the slide I showed twice about what the role of the curator, think about. I wrote the machine entity, right? I see them as valid and eye-to-eye level collaborator in this process. So I just don't think that they can right now do a project without us, right? But I think we both are completely at the same on the same board. Cool, thank you.
Yeah, can I go ahead?
Hello.
Yeah. Fantastic. Thanks a lot, Benjamin. Fantastic stuff. I'm curious. So my question is related to noise. Like, what's your angle on that? Because, for example, with these latent diffusion games, huh? So, like as an example, just to think of there was a Pokemon GAN that was pretty popular
Yes.
when it came out. And then now, if you Google Pokemon, you get 1 billion Pokemon, you get Pikachu, you get this, that, etc. And then you get hundreds of latent ones as well. But then I'm wondering, but still Pikachu has a presence. Pikachu has a legacy. Pikachu has an indexicality to the multiple stories and the amount of times it has appeared on screens. People have a relationship to them. And then to kind of relate that to this idea of the hybrid, I'm curious about that because I would think that a hybrid would be something that keeps paradoxes alive. So you would be able to identify certain sensibilities of the things that it is comprising of. Then when we go to the latent space, things get blurry, things get dissolvable. I'm wondering with these very beautiful, colorful models that you have, what would be an angle of indexicality in them? Would it be possible to kind of trace a legacy from them? What would it take to make them a thing rather than a blend? You know what I mean?
I think you know what I know what you're talking about. I'm not 100% sure about the Pikachu example, but I know of Pikachu, and I'm not the most knowledgeable about that. But what I think is important to point out, and what you mentioned, like at the first Pokegon, that it was not quite there, and the results were lacking fidelity, but it was a good start. Once we're in this latent space, right? And once we are extracting, I would say, a certain state or a walk through this latent space, like shown in Convoluted City, we need to rethink how we read that. And I think we both agree on that. How we specifically would make an indexed legend, right? I don't even know if that is even possible, right? Because Convoluted City, if we see it as a different cartography of all different kind of maps and satellite imageries that we lay on top of it, how would we be able to make even a legend of that? Because if I take a different latent walk, the legend might be a completely different. So I potentially resort to Carla, and we might rely and just accept, for now at least, that the machine does its job right and that everybody is represented properly. Another angle to it is certain GANs do not just equalize data, but they also learn high-level and low-level features, right? Especially all the style GAN, not the style transfer, but the style GAN that I show with the faces and that we also use for these latent walks, where compared to a face or to a building, the shape, the overall composition, the outline of these data sets are kept very precisely. But then small nuances, like if I'm smiling, if a building is brick, if a building is concrete, these are then other types of high-level features which can then be sampled or directly be called out. So I would say the best way to do this, or creating the legend or indexical kind of approach towards this, is to use, again, another AI system that tells me what kind of features are most prominent, or a kind of a way to call specific, like a smiling or a brick building with more control. We haven't achieved that yet, to be honest, but I could see a lot of very interesting and also useful applications in terms of research also. I don't know if this answered your question, but that's what I can. Please, yes.
If you go to Deleuze and Guattari, the definition of a diagram is that it doesn't contain anything that exists before.
Right.
So it only contains what can be drawn out of it, in other words. And it's not a thing, it's an operational existence. And so if you take these as being somewhere not quite indexed, like a Pikachu, but also, and maybe the point is not to index them at all, but to actually engage interpretation. So I think the next steps in your diagram might be to go beyond an output and
Right.
into a second phase of curatorial or interpretational, not linguistic, it's meta-linguistic, actually, with that as source material. I think you need AI, like you were just suggesting, to pull seeds out of that. In other words, our ability to see the thing is limited to a moment in time. We can turn it, we can move it around, we can try to probe it. Ultimately, it's how we sense the thing that
Right.
gives us the information we need to take it a step further. But I think that's really where these lie.
I love that we should talk. Thank you. There's one more question over there.
I wanted to thank you for the presentation. It was really, really informative. But I have a question on if there's some sort of sustainable approach that can be adapted into the technology. Like if it's adapted into the technology, how would that affect the outcome? Would the outcome still be as beautiful and as kind of abstract as it is, or will it start to simplify the outcome a bit more? How do you think that?
Very good question. I think it goes a little bit what we already talked about. If it's going to be as beautiful, I don't know, but that's not the important point. But we certainly can, for example, Convoluted City, at least start with an idea of like, the place we live in is not always the place where we draw our wealth or generate our waste landscapes and whatsoever. So incorporating more sustainable, and I mean, I would rather say resilient ideas towards feeding the data, definitely would be fantastic. I mean, I even in the early attempts, right? Let's imagine Barcelona gets like 10 degrees hotter, which it won't, right? But how can we retrofit the Barcelona block in the fashion of with Marrakesh courtyards to make a more resilient urban infrastructure, right? Yes, I think we can. I haven't talked much about that, but I'm aware, and I think we need to do that. Yeah, beyond just making everything beautiful. I didn't consider to come across like a formalist, but maybe it's because I showed Wolfland. But I appreciate it. I think you're right. It's very important. Thank you. Yeah.
Someone else, I always forgot.
Michael.
I have a question regarding what you're talking about designer and prompt engineer, and I don't know if you already started talking about this, but when you create the 3D GAN models, how much integration do those geometries have with, say, like other 3D modeling softwares?
Very good question. So the very first one that where I tried this 3D GAN process, like the house Yamitsky, when you see all the furniture and the mullions and stuff, the GAN didn't give me that. What the GAN gave me was the rough outer and interior shell, because that's all I was able to train it, right? I was also not able to train much of materiality, much of like, segmentation of architectural elements. Later on, we're just getting better and better, where we can feed more underlaying and nested multidimensional information per voxel, which potentially will yield to also an increased fidelity. We are by far not close to any fidelity what diffusion models have in terms of like realism and output. But that's also not really the goal for now, because my critique also not critique, but I think that there is a discussion around diffusion models, which is the exact same scenario of what I showed from 2017 at UCLA using style transfer. At the end of the day, you need to sit down and you need to model it by hand, okay? So if we take that into a practical application, because Midjourney right now in widespread, also in Texas, local office, 3-people office, they use Midjourney to show these outputs to their clients immediately, right? The problem is when they say, I want that. We haven't jumped the loop of like taking away the laborer's process. Right? Exactly. Figuring that out, right? The thing about Convoluted City, why I'm mostly excited about that project is that latent data goes directly into physical matter. There's no 3D modeling in between, right? And I think that's also one of the other holy grails. If we can achieve that, we're gonna be billionaires, or we're gonna have a very nice life as architects. I don't know. Does that answer your question? Sorry. Yeah. Thank you for asking.
Can I just jump in very, very
Yes,
quickly? So
please.
you said, like, okay, they have an office and they use Midjourney. They say, okay, I want that. My question is, what is that they want? Is it a product? Because a product usually, being a product, to be successful product, you have to sell that. You have to market it. You have to go through an incredible amount of steps of trying to convince people to buy something. Or you need to say what it is. What does it relate to? What does it bring to you? And when I look at the output of Midjourney, it's nice, but it's mute. It doesn't talk anything. It doesn't suggest anything. It just looks. So how do we go about that?
I completely agree, but I think it also comes back to depends on your client, right? If I just want to have I would say off-the-shelf house in rural Texas or wherever, and if you show me that image, or you show me the image of my neighbor, I equally tell you I want that. Maybe not my neighbor because that looks suspicious, right? But 3 blocks down, I will take the exact same building. You know what I mean? Again, it depends where your client is in a specific example, but also it goes down to what can we even generate with these models when they are only trained on popular culture, right? Because obviously, if you ask for in the style of Frank Gehry or Zaha Hadid, you will get very close results. If you ask in the style of Benjamin Ennemoser, you get crap because I'm just not famous, right? Because I'm not represented in there. So it again comes back to bias, right? Like, what do you want to sell with these images? I don't know if this answers the question, but yeah, but I think I think we should also think about that. Yeah, thank you.
Does this also speak to for the importance of metadata on images? So I'm actually trying to think, because I'm not working in this area, I'm a historian primarily, so I'm trying to think about, do we have to ask our students to, when they post images of buildings or kind of cultural landscapes, to embed them with some historical data that then can be used by a machine to produce things? There is the Society of Architectural Historians has the Archipedia, which is an encyclopedia of historical architecture and comes all the way to the present. But I actually don't know if their images are usable, or if that's an archive that can be used for something that has more historical depth as well, or meaning.
Right, I think I agree. And the funny thing would be, if we all would do that, we could bias the system towards a better or worse way. But yes, if you want to know what these diffusion models are mostly trained on, or at least for the biggest time of their existence, which is not that long, the way that we are using in Midjourney, just go online, go to Lion dataset, LAION, and then look for cats, look for architecture, and it will spit you out all the labeled metadata and images that it's trained on. It also gives you a very good understanding why certain keywords work so much better, right, than others, or why we as architects sometimes need to resort outside of our I would say comfort zone in terms of terminologies, and borrow from other disciplines to get what we want. Like, I remember, like, in the first couple of versions of Midjourney, V1, V2, in order to get something, I would say, that I formally think is more appealing or pleasing, you always had to use mycelium, right? Because it was trained on tons of my images of fungi and mycelium, and then it made you some more curvilinear, right, structures. That also has changed, right? I mean, as far as I know, generating or asking for architectural plans is still horrible. I haven't tried it since a couple of months, but I still think Midjourney is still really bad. It looks like a plan, but it doesn't make sense at all. But it might have changed in the last 2 months. Okay, I think. Thank you. Oh.